So now that we've covered the key methods in the Java ForkJoin pool class, let's talk about the key methods in the Java ForkJoinTask Superclass. And this will go into a bit more refinement of what we had talked about earlier when we talked about the hierarchy of classes and generally what this thing did. So ForkJoinTask implements future, as you can see here. And as a consequence of doing this, it gets all the methods that are defined in future. And remember, there's about a half dozen or so methods that come in modern versions of future that we care about. It's not very common to use these methods in the future class, but they're there, so you need to be aware of the fact that they are there. There are three key methods that are defined in ForkJoinTask. These are the ones that actually count, that matter. You will use some of these in your implementations for the assignment. So the first one is fork. And fork is used to enable a task, which is the parent task, to create one or more subtasks that will run in parallel with either the parent task and or the subtask. So that's what fork does. You can see it returns a fork join task. And this arranges, it doesn't start running this immediately, but it arranges to execute this task asynchronously in either the current tasks pool, if we have a special instance of fork join task, or in the common fork join pool. And so you'll see that this basically kind of queues things up. We'll take a look at that later when we look at the implementation. The fork method does not block the caller. What it really does is it just makes a message, and it sticks the message onto a queue, and then that queue will be run by some thread in the common fork join pool at some point, hopefully in the very near future. And the way it works is the call to fork pushes the task, or the subtask, maybe a better term, onto the head or the front of a double-ended queue that's owned by the current worker thread. So whatever thread you call this in, whatever that worker thread is, that is what's going to have its deck, and then that is what's going to use it. Now, keep in mind that this assumes that you're in the context of the fork join pool. Whenever you have a non-fork join task client, it needs to use a different method like invoke, submit, execute, and so on. But once we're into the fork join pool, then when we do a fork, that creates essentially a data structure, and it pushes it onto the head or the front of this double-ended queue. That's very important to remember, the head. We'll talk more about why that is important later when we talk about the internals of how all this stuff works under the hood. Join, in contrast, returns the result of a previously forked computation when it finishes running. And as you can see here, join is going to return a value of type v, which is parameterized as the parameter to the fork join task. So that's the return value. V is for value. V is not for vendetta in this context, it's for value. What will happen here is that whoever calls join, which is going to be a fork join worker thread in the fork join pool, whatever pool you're dealing with, common pool, special pool, and so on, will block, and I'm using the word block in quotes here, until the forked subtask is done. Now, what that really means is that the call to block won't return until we get the result of that fork join task that we call join on. However, it doesn't mean that that calling thread goes to sleep. Instead, what happens is the collaborative Jiffy Lube model of processing. And I think we've talked about this before, so I'll just quickly recap it. But in a nutshell, you have a pool of threads, which is like a pool of workers at the Jiffy Lube when you get your oil changed. And maybe you have one or two workers per bay. And when a car drives in, if you have all the bays full, then the workers will just work on that car in their bay. That's the normal way things work. That's a thread pool model, and if you've got n bays or 4 bays, then you've got groups of people working in parallel. However, in theory, if there's no other cars except one bay, when the car pulls into the bay, then the other workers from the other bays can come over and work on that car in parallel. So they can pitch in and help out, and therefore get things done faster. So that's kind of what happens when you call join. The calling thread pitches in and does other processing until it gets the result back that it was called on. This call, this join call, defines what's known as a synchronization point. And what that means is after join returns, the memory changes that correspond to anything in that core where the processing took place will be propagated to other cores on that processor. you don't have to do any additional synchronization yourself. So the fancy way of saying this is it ensures that all writes that take place to fields in a worker thread that happen before the join are made visible to the other threads in other parts of the pool after the join finishes. And that's what's called a happens before relationship. You can read more about that here. We will not talk a lot about happens before relationships. I have another class where we talk a lot about that. And you can see videos on that. If you Google happens before Java, Douglas Schmidt on YouTube, you should find the videos that talk about that. Invoke performs a task, awaits its completion if needed, and returns its result. So unlike fork and join, which are sort of inherently asynchronous, invoke is a more synchronous way of doing things that call and then wait for the result. We're not going to use the invoke method a lot in our examples, but just be aware that it does exist. If you call something and an error occurs, then a runtime exception can be thrown from the invoke method under the right circumstances. So that's the end of the overview in the Java fork join superclass.